Imagine a universe where most of its content is invisible. A universe where an enigmatic substance holds galaxies together and affects the very fabric of space. This isn't science fiction, it's the intriguing reality we face when we explore the mystery of dark matter. Join us on Cosmic Odyssey as we unravel one of the greatest enigmas in modern astrophysics. Our story begins in the early 20th century, when astronomers were meticulously studying the motion of stars within galaxies. They expected these stars to follow Newton's laws of gravity, slowing down as they moved further from the galactic center. However, what they observed defied expectations. Instead of slowing down, the stars at the edges of galaxies were moving just as fast as those near the center. This puzzling observation suggested that there was much more mass in galaxies than what we could see. This unseen mass became known as dark matter. But what exactly is dark matter, and why can't we see it? Dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, it exerts a gravitational pull that influences the motion of stars and galaxies. To understand its presence, let's dive deeper into the evidence supporting the existence of dark matter. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a collection of galaxies bound together by gravity. Zwicky measured the velocities of these galaxies and found that they were moving too fast to be held together by the visible matter alone. He proposed the existence of missing mass, which we now refer to as dark matter, to account for this discrepancy. Another compelling piece of evidence comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light. When we observe light from distant galaxies being bent and magnified by clusters of galaxies, the amount of bending indicates more mass than what we can see. This extra mass is attributed to dark matter. The cosmic microwave background radiation CMB also provides clues about dark matter. The CMB is the afterglow of the Big Bang, a snapshot of the early universe. Tiny fluctuations in this radiation, observed by satellites like COBE, WMAP, and Planck, reveal the distribution of matter in the early universe. The patterns we see in the CMB can only be explained if there is about 5 times more dark matter than ordinary matter. Computer simulations of the universe's evolution further support the existence of dark matter. These simulations, which model the formation of galaxies and large-scale structures, match observations only when dark matter is included. Without dark matter, the universe would look vastly different from what we see today. So what could dark matter be made of? There are several hypotheses, but the most popular candidates are WIMPs weakly interacting massive particles and axions. WIMPs are hypothetical particles that interact with normal matter through gravity and possibly the weak nuclear force. Despite numerous experiments designed to detect WIMPs, they remain elusive. Efforts to detect dark matter particles directly involve highly sensitive detectors placed deep underground to shield them from cosmic rays and other background radiation. Experiments like the Large Underground Xenon LUX and the Cryogenic Dark Matter Search CDMS are at the forefront of this quest. Although we've yet to capture definitive evidence of dark matter particles, these experiments have significantly advanced our understanding of what dark matter isn't. Particle accelerators like the Large Hadron Collider LHC at CERN are also involved in the hunt for dark matter. By smashing protons together at high energies, scientists hope to create dark matter particles and study their properties. While the LHC has yet to produce conclusive results, each experiment brings us closer to unlocking the secrets of dark matter. The Bullet Cluster provides another dramatic piece of evidence for dark matter. This system is formed by the collision of 2 galaxy clusters. Observations show that the visible matter, mostly hot gas, is separated from the mass inferred from gravitational lensing. This separation indicates that dark matter, which doesn't interact strongly with normal matter, passed through the collision unaffected, providing a clear distinction between dark and normal matter. Despite the overwhelming evidence, dark matter remains one of the biggest mysteries in cosmology. Its exact nature and composition are still unknown, and solving this puzzle will require innovative approaches and new technologies. Researchers are exploring alternative theories, such as modified gravity, but these models haven't yet provided a better explanation than dark matter. Future missions and observatories, like the James Webb Space Telescope and the Euclid mission, will continue to probe the universe's dark components. These missions aim to provide more precise measurements of dark matter's effects on cosmic structures, potentially leading to breakthroughs in our understanding. Dark matter is a fundamental component of the cosmos, influencing the formation and evolution of galaxies and the universe itself. It reminds us that there is still so much to discover about the universe we inhabit. As we continue to explore and learn, we inch closer to unveiling the true nature of this invisible yet influential substance. Thank you for joining us on this journey into the unknown with Cosmic Odyssey. Dark matter may be invisible, but its impact on the universe is undeniable. Don't forget to like, subscribe, and hit the notification bell for more cosmic explorations. Until next time, keep looking up and pondering the mysteries of the universe.